check. All right, the audio slash video looks fine, and we are a little early, like 2 to 3 minutes early, which is fine since we have some stuff to cover today. So ideally, we should be done with error analysis by tomorrow, and if we do not delay things, then we should be able to complete it. So welcome, guys, to this bridge course. We are running a session in physics. Basically, as I've already told you, this course is for people who have finished their 10th and are about to start their preparation in 11th. And there are certain basic concepts which are present throughout all 11th, 12th chapters, which are to be mastered. And this bridge course is exactly meant for that. So even guys who are in class 9th or 10th, who have not finished their 10th yet, and people who are in 11th, 12th and are still struggling with a lot of chapters, excuse me, that's probably because you guys still have some problems in your basics. You know, the guys who are struggling in 11th and 12th in a lot of chapters, most likely you still have some problems in your basics. So this series will be useful for you because we are covering all basic topics in a slow fashion and in an exhaustive fashion. Like, we are covering everything that's required from the exam perspective. So you guys can join in too. People who are in 9th and who want to learn some basics so that their 11th, 12th maths or physics gets stronger, you guys are welcome to. But as I've said, it's specifically designed for people who have finished their 10th and are about to start their 11th preparation. Never mind, we have already finished dimensions. We started error analysis yesterday. We had an intro to that. Today we will jump right into it and study the chapter in more detail. So we are starting exactly at 12. Let me see if I have some people in the live chat. So as I've told you, you guys can always, type in your doubts, interact with me whenever you come live. And obviously this advantage you'll have only if you come live. If you're watching a recorded lecture, I cannot really interact with you except through comment section, which again is not interactive as a live session. So fine, let's begin. So yesterday I told you that any quantity in physics, whether this quantity is length, whether it's mass, whether it's volume, any quantity in physics, whenever it's measured, it's reported as a most probable measurement plus some error associated. What does this mean? This means that it's not really possible for us to measure any physical quantity to complete accuracy. Like, we will obviously commit some mistake or the other, because of which there will be an error associated with your measurement. And whenever you report a measurement, you have to account for it with the error. So number one, I can see three things here. This is the first quantity, this is the second term, this is the third term. Let's see what each of these three terms are. Number one, first term is your physical quantity. This quantity can be anything. It can be mass, it can be volume. As I told you, it can be any physical quantity that you're trying to measure. Number two, what's number two? QM. QM is the most likely measurement. It's a term that I'm using on my own. It's not a textbook term. But what I'm trying to say here is, let's say you had some measurements like 9.95, 10, 10.05, and all those things. So you will account 10. If the least count, now I'm going to tell you what least count is. If the least count of the instrument with which you are trying to measure is 0.05, then the measurement that you will report is 10. So let's try to understand this phenomena in more detail. Hi Swati. So Number 3, what's the third term here? Third term is the maximum error boundary or error possible. So again, terms are not important, the understanding is important. So let me tell you, let's go like this. Yesterday we had a pencil, right? Now I'm a little better with drawing pencils quickly. Here you have a scale. Question to you, what is the least measurement that you can do with a pencil scale, pencil box scale? Pencil box scale means your Camlin scale, which is 15 centimeter long. What is the smallest measurement that you can do with that instrument? If you have observed closely, this is a 0. This is 1, 2, 3, 4. Fifth one is slightly bigger. 7, 6, 7, 8, 9. 10th one is this. 10th one is as big as this, right? Good afternoon, Astrid. So you have 0. You have 1 centimeter here, and this is your 0.5 centimeter mark, correct? Or 5 millimeter mark. But what is the least value that you can measure with the scale? It is this, and this is 1 mm, right? So 1 mm is the least that you can measure with this instrument. That's why it's called as the least count of this instrument. So least count is a very simple thing. Pick up any instrument, tell me the smallest value that you can measure with that instrument. That smallest value is the least count of the instrument. This error that you see here, is the least count of the instrument. Why? Why should this be the least count? So let's say using the scale you measured 26 mm, okay? But you can obviously do some mistake of 1 mm. It is possible. Why? Because you cannot do a mistake which is greater than 1 mm, because anything more than 1 mm is clearly visible to you on the scale. Like what I'm trying to say here is, this is a 0, this is a 1, 2, 3, 4, 5th, right? So can you do a mistake which is bigger than this? Obviously no, right? Because that will be visible by your eye. What you will not be able to account for is if there is, if let's say the object that you're trying to measure, let me draw a magnified version, okay, then it will be clear. So this is your 0, this is 1 mm, this is 2 mm, this is 3 mm, this is 4 mm, this is 5 mm, and this is 0, this whole thing is 0. 6, 7, 8, 9, and this is 10 mm, which is 1 centimeter. Okay, I'm zooming into this. This is the zoomed version. Okay, let's say your object is of this much length, right? This is your object. Let me draw the object using red color. Now can you see this object is falling between these two? That means I know for sure that my object is more than 2 mm, but it is less than 3 mm, right? If this object was bigger than 3 mm, then obviously you would say that object's length is between 3 mm and 4 mm. So the maximum error that you can do is the least count of the instrument. You cannot do an error more than this, because anything more than this will be visible by your naked eye, right? So I will say that the length of the object, let's say if I measure 26 mm, I will report 26 mm as 26 plus or minus 1 mm. This 1 mm is the least count, or it is the error, and this is the most likely measurement, or like, let's say, what is, let me just take, what is it called? Is there a term that I'm trying to miss? I'm just seeing that. Okay, there is no specific term given in the book for this, so that's why I would just say most likely measurement. Just understand it like this. Don't write it in your board exams, but understand it that way, that this is your most likely measurement. So your scale's length could be anything between 25 mm to 27 mm. Like if you do 26 minus 1, you will get 25. If you do 26 plus 1, you will get 27. So your scale's length can be anything between these two. But what we know for sure is that the length of the object 26 mm. If your most probable measurement is 26 mm, what we know for sure is the length of that object cannot be less than 25 and it cannot be more than 27. It's definitely between 26 and 27, because if it is less than 25, if it is actually less than 25, then you will obviously be able to see that on the scale, right? You will be able to see. The only length that you will not be able to differentiate between is if that boundary is 1 mm or less than that, right? So if 26 mm is here, the maximum uncertainty that you can have is that of 1 mm on both sides. Are you getting my point? The maximum uncertainty from 26 that you can have is 1 mm on both sides, because anything more than 1 mm will be visible by your naked eye. So that is the point that I was trying to make. So the rule that you have to go away with here is any physical quantity is reported as its most probable value or most likely measured value plus or minus the error associated, and this error is usually dependent on the least count. In fact, it is the least count of the instrument. I should say it is the least count of the instrument that you are measuring with. Right? So I hope I made some sense here. All right. So moving forward, next question to you. Why do these errors occur? Why? Why can I not say that this QM is exactly accurate to the actual length of the object? Why should I always account for the error? Or in other words, why does this error always come? So these errors come because of two reasons, or I can say this error is of two types. One is systematic errors. I was confused with systemic errors. It's not systemic errors. And the second is random errors. So I'll just define these two. I'll not write the definition. You can just understand it. I'll just read it from the textbook. Systematic errors are the errors whose causes are known to us. Such errors can be minimized. You can control these. The point is, you can control these. So let's say if your instrument has a fault, like if you know that your scale does not start from 0, like let's say your scale, which was initially starting from 0, then it had 1 centimeter, then it had 2 centimeter, then it had 3, like that, and then in the middle all these were there. Let's say this part came off, this part broke. So now your new scale will start from, your new broken scale will start from 1, isn't it? So if you are taking an object of 2 centimeter, if you take this object and you place it here, now this spoiled scale will show me 3, correct? Because the spoiled scale is starting from 1, no. So it will show me 1 centimeter extra measurement because it's a broken scale. So this type of error, there is an error of 1 centimeter, which is a huge error, right? By the way, 1 centimeter is a huge error. Usually this delta Q is very small compared to QM. That's how it's a, that's the usual case. Now I can't say that the length of the the object that I'm trying to measure is 26 centimeter plus or minus 1 centimeter. No, this does not make sense, because this cannot be of the order of centimeter. If this is of the order of centimeter, this has to be of the order of millimeters or less, because your error cannot be of the same order as the measurement, right? That does not happen. Usually errors are very small. So here in a broken scale, the error is coming in the order of the length of the object. Like object is of 2 centimeter length, and the error that I'm getting is of 1 centimeter. Like it's showing me 1 centimeter more. So that's very huge. Usually you don't have such errors. But that error has come because of the fault in the instrument. So can I not consciously, when I measure it using this scale, what I can simply do is, whatever length I get, let's say I get 3 centimeters, so I'll subtract 1 centimeter from this, and I will say that the actual length is 2 centimeter. So in a way, I can minimize that error in the measurement, right? If I know the fault in the instrument already, I can consciously, in my measurement, I can take care of that fault, and I can minimize the error in the measurement, correct? Other causes of systematic errors, let's see. Some errors arise on the account of ignoring certain facts. Let's say when you're measuring the time period of a simple pendulum, error may creep in because you did not take care of air resistance. So when we, this formula that you see, P is equal to 2 pi root L by G, you should know that this does not account for air resistance. I hope you know that. Or maybe you wouldn't know because you don't know how it's derived. But this formula assumes that my pendulum is in a space where there is no air. Only then the formula of time period will be 2 pi root L by G. If I account for air resistance, then the formula will not be this. Then the time period that you measure using a clock will be slightly different from what you get using this formula, right? And that error will come because you did not account for air resistance. So if you know that you have not accounted for air resistance and that's why the error has come, then you can account for it and you can try to minimize the error, correct? So all these errors whose causes are known to us, so these are known to us, systematic errors, we know the cause of these errors, so we can obviously control these. To an extent, we can minimize these errors. But random errors causes are unknown. Hello Surya, good to see you. Looks like you are coming here for the first time. It's great to see new people coming in every day. Looks like you guys are liking this course and I'm quite happy about it. Okay, so the causes of random errors are not known. Hence, it is not possible to remove them completely. What is one such error? Like let's say I have this pen. I take a scale and every time I try to measure the length. And every time I measure it, I will get a slightly different length. Like let's say one time I'll get, and especially if I'm trying to measure it using a very precise instrument, not even using a scale, using an instrument which can measure up to very small precision. If I measure this using that instrument, then I might get 10.001 centimeters sometimes. I might get 10.002 centimeters sometimes. I might get 9.998 centimeters sometimes, which means every time I measure, I will get a slightly different length. Now, why is this happening? There is no fault in the instrument. There is no factor that I'm ignoring. I'm taking air resistance or every factor that's possible, but still these errors will come. That is because we are humans. Our hands, our eyes, everything is like not accurate, not fully accurate. We will obviously commit some mistake when we are handling high precision instruments. So the errors which come because we are humans, those kind of errors are usually random errors. I shouldn't exactly say this. I should say that the errors which come because we can't help but to commit those. They occur because of nature, because not everything is perfect. But we still don't know why those errors exist. We just know that they do exist. So those errors are random errors which will come in randomly. Causes are unknown, and hence you can't control them. And these errors that we try to report, usually these are random errors. Hariharan, hi. Error, what, sir? Well, Hari, the whole chapter has been about errors, so I don't quite understand your question, what you're trying to say. And if you're not understanding what's happening here, maybe that's because you have missed the introduction yesterday and you joined in late today. So you may go and watch 15 minutes, the last 15 minutes of the previous class, and then start from the beginning of this class, and then come here. You'll understand. So, guys, I hope you understood. This Q is equals to QM plus or minus delta Q. This delta Q that you see is usually a random error that we account for. Because if this was a systematic error, we would have removed it. No. Systematic errors causes are known to us. So we can work on those causes and we can try to minimize, or we can also remove them. But random errors we cannot, and hence this delta Q we'll have to report it with this random error. Whatever we measure, we'll have to report it with random error. So then what we do is, let's say there is an object of length, I don't know its length, but I'm trying to measure it using a scale. This is my scale. This is my object. And let's say the first time I measured it, I got A1 as the length. I'm measuring lengths, okay? Let's say the first time I measured, I got A1. The second time I measured, I got A2. The third time I measured, I got A3 as length. Likewise, when I measured it for the nth time, I got AN as the length. So every time I measured, I got a different length. Why did that happen? Because we are humans, we will most likely commit some mistake, and hence we will get some random errors in our measurement, because of which every time we are getting a different measurement. So what you will do is, you will first take the mean of these. How will you take the mean? How will you take the mean of n quantities? You will just add them and divide it with number of trials, right? So that way you will get AM. AM is the mean of all these measurements. So this mean is what we will report, but along with the mean we will report for some error, delta A. So we will say that the actual length A is nothing but AM, which is the mean of all these measurements, plus delta A, which is the error. So what is this error? This error can be of various types. First of all, it's random errors, but it can again be of various types. So random errors you have understood. Whenever you have measuring, you'll get errors randomly, right? And then because of that, you will have to report for the mean of all these along with the error. Next, what we have is absolute error. So we will discuss the types of errors now, right? Types of errors that you can calculate. Let me just put the heading. I would just like to make a slight modification to what I said yesterday. Sorry, what I said just before. Like this delta A can be of various types. We are just trying to discuss the types here. Types of errors that we can calculate. Not all of these are useful to us, but there are a couple of these which we extensively use whenever we report. So number one is Riddhi. Hello Riddhi. Again we have a new person. So 1, 2, 3, 4. There are 4 types of errors that I'll tell you about. I told you about random errors already. And whenever we randomly carry out experiments, we'll get different measurements, and we'll just have to take the mean of all those, and that's the report. That's the value that we will report along with the error. Next, we have absolute error. what is this error? What is absolute error? So you had these measurements A1, A2, A3, so on up to AN. When you carried out the experiments randomly, you got N measurements, and then you took the mean of all these, which was nothing but A1 plus A2 plus so on up to AN divided by N. Correct? You got the mean. Now, absolute error. What is absolute error? There are N absolutes error here. There are N absolute errors in this situation. So with the first measurement, there is an error associated. With the second measurement, there is an error associated. With the third measurement, there is an error associated. With the nth measurement, there is an error associated, which means with every measurement, there is an error associated. How will I calculate that error? Delta A1 is nothing but take the mean value and subtract A1 from that. That is the absolute error associated with A1. Getting it? What will be the absolute error associated with A2? Delta A2? It's nothing but AM minus A2. This is the absolute error associated with A2. What is the absolute error associated with A3? It is AM minus A3. This is the absolute error associated with A3. What is the absolute error associated with AN? It is simply mean minus the measurement. So whenever you want to calculate the absolute error associated with some measurement in a pool of random measurements, then you take the mean of all these random measurements and subtract this measurement from the mean to get the absolute error associated with this measurement. Making sense? So this is the absolute error. This is legibility problems. Absolute error associated with AN. Right? So this was easy. So this is the whole picture. First we started a random experiment, right? And we got a lot of errors, right? Because every time we got a different measurement. So there are random errors obviously in this experiment. Next we saw the absolute error associated with each of these measurements. Next we will see mean absolute error. Just give me a minute, guys. Right. So we saw this. Now let's see what is mean absolute error. So when you take the mean of all absolute errors, it's not meant, it's mean. When you take the mean of all absolute errors, you get mean absolute error. So don't get worried right now. Like I'm first teaching about each error, and then I'll give you the whole picture towards the end. Like why are we studying this and what is the whole story? Just keep following with the story. Don't get scared. Why did we study absolute error? Why are we studying mean absolute error? Next we will see fractional error. Why will we study that? Don't get scared by all that. Just keep following with me, and then I will give you the whole picture. Once you understand all these four, then we will look at the whole picture. And tomorrow we will do some problems. Today itself we will do if time permits. Okay. Now, in fact, I should write when you take the mean of the absolute value of all absolute errors, then you get the mean absolute error. So keep following with the story. You had a lot of measurements, A1, A2, A3, A4. These are not points, by the way. These are measurements that you, like one of them could be 9.98. The other could be 9.99. One could be 10. These are different values of the quantity that you measured. So A1, A2, A3, A4, so on up to AN you measured. Okay. Then you calculated the absolute error associated with each measurement. So absolute error associated with A1 was this. Absolute error associated with A2 measurement was this. Absolute error associated with A3 measurement was this. Absolute error associated with AN measurement was this. Now what I want you to do is take the absolute value of all those absolute errors and add them. So take the absolute value of A1, add that to absolute value of A2, add that to absolute value of A3, and add that to absolute value delta A3, sorry, not A3, and add that to absolute value of AN. Looks like I hid. Let me just pause my video for a while. Right, it's visible. And divide this whole quantity with N, which means take the mean of absolute values of all absolute errors. If you do this, then the quantity that you get is called as mean absolute error. Okay. So we saw the third kind of error also. So once again, I'll bring all three together. So when you carried out a random experiment, you got a lot of measurements for the same object. You got a lot of measurements. Okay. Then you conclude that there are some random errors in this experiment. All right. So first of all, what is the closest value that you will report? You will report the mean, AM, which is the arithmetic mean of all these measurements. Then we calculated the absolute error associated with each measurement. Like delta A1 is AM minus A1. Delta A2 is AM minus A2. Delta AN is AM minus AN. We calculated the absolute error associated with each. Then what we did is we took the absolute value of all these absolute errors, and then we took the mean of all these absolute values. Then we got mean absolute error, right? So we took delta A1's absolute value, we took delta A2's absolute value, we took delta AN's absolute value, we took the mean of all these, and that is my mean absolute error, right? So all this is coming from the same experiment, right? All this is coming from the same experiment. Don't think that different errors are for different experiments. Now we will look at the final fourth error, and this is the relative or fractional error. Make sure you understand all these errors properly, guys. Okay, because only if you have a proper understanding, then you will know what each and every term in a reported measurement means. Unless you have full clarity about these four, you will always have some doubt. Okay. So before we even start 4, let me tell you what happens? What happens in a laboratory? So now we are getting to practical stuff. Why are we studying all this? You had an object. Let's say you want to measure its length. You took a scale. You started measuring. Okay. You measured. First time you got the length as A1. Next time you got A2. Then after n trials, you got AN. Right. Every trial gave you a different measurement. Then you know that these are all random errors, because whenever you carry out an experiment, we are humans, we will commit some mistakes, and these mistakes are known as random errors. Now, we will first calculate the mean of all these measurements. And we will say that this is the most likely measurement, like the closest value that I can report with a certain accuracy. That's how I wanted to understand it. Again, don't go by literal terms. You will calculate the mean. Next, what you will do is you will calculate the absolute error associated with A1. I'm telling you what a scientist will do in a laboratory. I'm telling you that. So after getting the mean, the scientist will get the absolute error associated with A1 using this. He will get the absolute error associated with A2 using this. He will get the absolute error associated with AN using this. Then what he will do is he will take the absolute value of all these absolute errors, and he will take the mean of all this, and he will say that this is AM. And then when he finally reports the length, this is not AM, this is delta A mean. This is delta A mean, okay? And when he finally reports the length, he will say that A's length is nothing but AM plus or minus delta A mean. This is what he will finally report. He will finally report this. Now you understand what this error means? Now let's go back. This AM, first of all, why does this expression exist? This expression exists because we did not get the same measurement every time. That is why we have to report it like this. So what is this AM in this? AM is the mean of all these measurements. What is delta A mean? To get delta A mean, I have to get absolute errors. To get absolute errors, I should first know the mean and value of each measurement. So now you completely understand how a measurement is reported in physics, right? It is reported using these two terms. Apart from this, there is also another type of error, and that is known as relative or fractional error. Let's look at this fourth error. In fact, to report a measurement, these three are sufficient. You don't need the fourth one. You don't need the fourth one to report a measurement, because from random errors, when you get absolute errors, and once you get mean absolute error, that is enough. It's a different thing that to get mean absolute error, you should first calculate absolute errors. Without calculating 2, you can't calculate 3, right? But once you get 3, then your job is done. All that you have to do is say that A is equal to AM plus or minus delta A mean, where this delta A mean is 3, right? I was writing something. Let me hide my voice. Oh, okay. You were able to see it. Fine. So your job ends here. However, if you want to represent the error in terms of percentage, then you will need this fourth type of error. Okay. Are you understanding? I can say that an object's length is 2 centimeter plus or minus 1 millimeter, or I can also say that an object's length is 2 centimeter plus or minus some percentage, right? I can also represent this error in terms of percentage, and to get that percentage we need this fourth term, which is relative or fractional error. And let's discuss that now. How will you get it? Simply, relative error. Relative error's formula is very simple. It is nothing but delta A mean divided by AM. That's all. You know what AM means? AM means mean of all the measurements. Delta A mean means absolute mean error, which was the third quantity that we had calculated. This quantity is delta A mean, and you get the mean by taking the arithmetic mean of all the measurements. When you divide delta A mean with mean, you will get relative error. That's all. And how will you get fractional error? Or this relative error itself is fractional error. This relative error itself is fractional error. How will you get percentage error? That's what it's called. How will you get percentage error? You will just multiply this quantity with 100, and then you will get percentage error. So sometimes you can report the percentage error, right? Instead of reporting it in terms of absolute mean error, you can also report the measurement in terms of percentage error. Let's try to understand this concept using a problem. Okay. We will quickly discuss a problem and then we will close for today. Tomorrow we will start with combination of errors. So guys, if you had any confusions regarding these errors, go back and revise it. Anyways, I think this problem should be able to clarify things further. So diameter of a wire is measured as 2.60, 2.620, 2.625, 2.630, 2.628 and 2.626 centimeter using a screw gauge. Calculate A, mean value of diameter. B, calculate absolute error in each measurement. C, calculate mean absolute error. D, calculate fractional error. E, calculate percentage error. And finally, express the result in terms of percentage error. So that's the question for you. Let's try to first understand the question. We had a wire. A wire has a certain diameter. It's a very small diameter. Just take a wire, imagine how small its diameter will be. To measure diameters which are that small, we need something like a screw gauge. We can't use a scale to measure such small lengths to that, and especially we can't use a scale to measure it with good precision. So we need a screw gauge. Screw gauge is a device that we will see later on. It's used to measure these small quantities. But using a screw gauge, when I did 5 measurements, every time I got a different measurement. 1, 2, 3, 4, 5. All these 5 trials gave me different measurements. Why did that happen? Because there are random errors associated with this experiment, because we are humans and we will commit some mistakes, right? So first what I will do is, I always have to get the mean of these. Whenever I want to report the final result, A is I want to calculate the mean of all these. So how will you calculate the mean? Let's say that mean is AM. How will you calculate it? It is 2.620 plus 2.625 plus 2.630 plus 2.628 plus 2.626 divided by 5. When you do this, you will get the means value as 2.6258 centimeter, but you have to round it off to 3 digits. Why am I rounding it up to 3 digits? Because all my measurements were in 3 digits only. No, all my measurements only had up to 3 digits. So even if my mean is coming up to 4 digits, I will have to round this to 3 digits. And how will you round it off? When you have 6.6258, then this 58 is rounded off to 60, right? That's, basic 10th class rounding off. So you have to round it up to something. You got the mean value. A part of the question is done. Coming to B part. Absolute error with each measurement. Very simple, right? B. Absolute error associated with each measurement. This is your A1, this is your A2, this is your A3, this is A4, this is A5. I need delta A1, which is absolute error associated with A1. I need delta A2, absolute error associated with A2. Like that, I need delta A5. So how will you get delta A1? Simply AM minus A1, correct? Which means 2.626 minus 2.620, which is 0.006 centimeter plus, correct? Plus 0.006. Let me hide myself. Let me hide my video for a while. So when you subtract these, what do you get? Plus 0.006 centimeter. Delta A2 is nothing but AM minus A2, which is 2.626. Same mean. Mean is the same for all these. Minus 2.625, which is plus 0.001 centimeter. How will you get delta A3? That is AM minus A3, which is 2.626 minus 2.630, which is minus 0.004 centimeter. It is 0.004. No, it is 0.00. Yeah, it is minus 0.004 centimeter. How will you get delta A4? AM minus A4, just calculate that and you will get it as minus 0.002 centimeter. And finally, AM minus A5 is what your delta A5 is. And when you calculate that, you will get 0.000 centimeter. Because AM and A5 are equal to each other. A5 is 2.626, AM is also 2.626. Correct? AM is also 2.626, A5 is also 2.626. So you'll get 0. So this is how you get the absolute errors associated with each measurement. Now, let's add a slide. Go back to C. What was C? C in the question is, get me the mean absolute error. How will you get the mean absolute error? To get the mean absolute error, which is your delta A mean, this is your mean absolute error. To get this, you will have to take the absolute value of all the absolute errors associated with each measurement. Now I think it's making some sense for you. So this is nothing but 0.006 plus mod of 0.001 plus mod of minus 0.004 plus mod of minus 0.002 plus 0, because the fifth delta A5 is 0, divided by 5. And this is nothing but 0.006 plus 0.001 plus 0.004 plus 0.002 plus 0.000, which is 0, divided by 5. And this will give you 0.0026. And again, there are 4 places here. You have to round it off to 3 digits. Because all your measurements, all your errors are in 3 digits, correct? All your absolute errors are in 3 digits. So mean absolute error also has to be in 3 digits. That's all. Now, if you want, you can happily say that the diameter of the wire is nothing but mean plus or minus delta AM. You can happily say it. You can end the discussion here. Like mean was 2.626, right? So you can say it is 2.626 plus or minus 0.003 centimeter. End of story. You can report this. But the question doesn't want you to do this. The question wants you to report it in terms of percentage. So I'll have to go one more step. I'll have to get relative error, which is the D part of the question. To get the relative error, it is simply delta A mean by AM. That's the formula. This is your relative error or fractional error, right? So delta A mean, just now we calculated in the previous section, it is 0.003. This is your delta A mean. And AM is nothing but 2.626, correct? And obviously you'll have to use a plus or minus always. All relative errors and means, like both D and C. For C also you'll have to put a plus or minus 0.03, and finally we are using it. Finally we are using a plus or minus only, right? And even for fractional error we will do that. We'll use a plus or minus, because you can either measure more or you can measure less, right? Whenever you're trying to measure a quantity, you can measure slightly more than that quantity, you can measure slightly less. So that's why plus and minus, both you will have to account. So when you carry this out, you will get plus or minus 0.001. Again, you'll have, it's not exactly this, it's something slightly more than 0.001, but you'll have to round it off to 3 digits, right? So I'm rounding it off to 3 digits and I'm saying plus or minus 0.001. This is your relative error. Number E, what is your percentage error? Because finally you have to report it in percentage. No, that's the F part of the question. So to report it in percentage error, I'll have to first get percentage error, which is nothing but relative error into 100. We saw the formula already in the previous section. Just take the relative error, whatever it is, delta A mean by AM, and multiply that with 100. This is relative error only, no? So relative error into 100, that's your thing here. So that's why you have plus or minus 0.001 into 100. And when you do that, you'll get plus or minus 0.1%. Correct? That's all. Now F part is all about reporting this. So you can say diameter of wire is nothing but 2.626 plus or minus 0.1%. And obviously we know that this is in centimeter, okay? So 2.626 centimeter plus or minus 0.1%. This is how I report it in terms of percentage. But if you want to report it in terms of absolute mean, you can do that also by saying it is 2.626 plus or minus 0.3 centimeter. This is also right. This is also right. This is representing measurement in terms of percent. This is representing measurement in terms of percentage error, and this is representing measurement in terms of absolute mean error, right? So I hope you understood the purpose of all the errors and how we go step by step to give a final measurement, right? And with this, we finish today's lecture. I hope you found it informative. If you have any doubts, you can put it in the chat. I will clarify. Otherwise, tomorrow's topic, tomorrow we will see combination of errors. For those of you who come to a fresh class, make sure that you revise the previous class and come, because as you see, I'm going slow, but I'm building from the previous class. So if there is any stuff from the previous class that you're not clear with, you will obviously have problems in attending the present lecture. Like, you will not be able to understand combination of errors properly if you do not understand today's class, right? Unless I go to a new chapter, as long as I'm in one chapter, you have to make sure that you are thorough with the previous lecture before you come to the present lecture. So for those of you who came today for the first time, if things did not make sense, go back and revise yesterday's lecture and then watch today's. Things will be clear, right? So with this, I will take your leave, and I hope you enjoyed the session today. And yeah, tomorrow we will start with combination of errors. Good to have you guys. Take care. Bye-bye and be safe.